In this video, we'll discuss how to use VSEPR to determine the shape of molecules. VSEPR is valence shell electron pair repulsion, and we use this to predict the three-dimensional shapes of molecules. And the reason that this works is because electrons have the same charge, they're all negative, so they repel each other. And due to this repulsion, atoms will arrange themselves in a certain way in a compound to minimize the repulsion between the electrons in those bonds. And so we have several different shapes, but we're going to look at five: linear, bent, trigonal planar, trigonal pyramidal, and tetrahedral. So in the first example, we're going to look at linear, and our example will be carbon dioxide. This will have two atoms bonded to a central atom, right? We have a central atom with two atoms bonded to it. We have zero lone pair of electron on the central atom. Look at carbon. Zero electrons. We have zero lone pair of electrons on carbon. And that's a bond angle of 180 degrees. So if we have carbon in the middle with a double bonded oxygen on one side and a double bonded oxygen on the other side, we can see that this is a linear molecule just by looking at it. So let's check the geometry. Yes, it's linear, and let's check the bond angles, and that shows us 180 degrees. The next example is the bent shape. Notice that it's very similar to the linear because you have a central atom with one atom bonded to each side of that central atom. We have two atoms bonded to the central atom. The difference, though, is that you have a lone pair. Because of this lone pair, it makes the shape bent. So we have our central atom, two atoms bonded to it, and then we have a lone pair. Notice what happens when you put on that lone pair. So you can take away the lone pair, you can add the lone pair, but that lone pair is what causes this to be bent. These electrons repel the electrons in this bond and the electrons in this bond. And the angle is 120 degrees. What happens if your molecule is very similar, but instead of one lone pair, there are two lone pair? So in the case of water, you have two lone pair. So you notice we have the same molecule from the other bent molecule, but if we had another lone pair, look at what happens to your bond angle. Yes, it's still bent. The shape is still bent. We're going to get rid of this one. We only care about the molecular geometry. It's bent, but the angle changes to 109.5. The next example is called trigonal planar. We have three atoms bonded to the central atom with zero lone pair of electrons. We have our central atom with three atoms bonded to it, and notice it's flat. The angle between each of these bonds is 120 degrees, so that's why it's called trigonal planar. It's like a triangle, and it's flat. It's on a plane, so trigonal planar. The next example is trigonal pyramidal. It's very similar to the trigonal planar, but look, we have a lone pair. So it's still three atoms bonded to a central atom, but now we have a lone pair. So just like the previous example, but now we're going to add a lone pair, and look what happens. It changes the shape. Now it looks like a pyramid. So instead of being trigonal planar, it's trigonal pyramidal. It's still like a triangle, and it's pyramidal shaped. The bond angle also changes to 109.5. The last example is called tetrahedral. That's where the central atom has four atoms bonded to it with zero lone pair with an angle of 109.5. We have our central atom with 1, 2, 3, 4 atoms bonded to it. And notice that it looks a lot like that trigonal pyramidal, right? But instead of having a lone pair on top, it has another atom on top. Same thing, 109.5. Okay, hopefully that helps.